Dober večer. Dobrodošli na današnjem znanstvenem večeru Univerze v Novi Gorici. V čast mi je, da predstavim profesorico Andrejo Gomboc, današnjo predavateljico. Andreja je izredna profesorica za področje astronomije in astrofizike na Univerzi v Ljubljani. Po doktoratu iz fizikalnih znanosti na Univerzi v Ljubljani pa je leta 2002 nadaljevala akademsko kariero kot Marie Curie Fellow na Astrophysics Research Institute, Liverpool, John Moores University v Veliki Britaniji. Na svoji raziskovalni poti se je ukvarjala z različnimi astrofizikalnimi problemi, kot so problematika črnih lukenj, določanje rotacijske hitrosti zvezd, ter v zadnjem času z izbruhi visoko-energijskih žarkov gama, ki jih lahko zaznamo s posebej za to konstruiranimi detektorskimi sklopi na satelitih ali na zemeljskem površju. Na aplikativnem področju se ukvarja tudi z modeliranjem satelitskega relativističnega navigacijskega sistema. Andreja ima več kot 60 referiranih člankov v mednarodnih publikacijah, med njimi 3 v najprestižnejših revijah, to je Nature in 2 v Science. Je prejemnik več znanstvenih in strokovnih priznanj. Njeno raziskovalno delo je bilo lani uvrščeno med 10 najodmevnejših raziskovalnih dosežkov raziskovalcev z Univerze v Ljubljani, ter med dosežke odlični v znanosti v ocenjevanju ARRS. Je prejemnik priznanja Prometej znanosti za odličnost komuniciranja in koordiniranje mednarodnega leta astronomije leta 2009 ter zlato priznanje Zveze organizacij za tehnično kulturo Slovenije za razvoj in popularizacijo astronomije. V nocojšnjem predavanju z naslovom Zadnji trenutki v življenju zvezd nam bo predstavila procese, ki so povezani z zadnjimi življenjskimi stopnjami nekaterih zvezd, ki ob svoji smrti lahko postanejo kratkotrajni, ampak izredno močni astronomski izvori svetlobe. To so na primer eksplozije supernov in izbruhi sevanja gama. Njihovo proučevanje povezuje različna raziskovalna področja, od zvezdne evolucije in dinamike do splošne teorije relativnosti in fizike osnovnih delcev. Tako da, prosim, Andreja. The lecture will be in English, so...
Good evening, everyone. Thank you, Samo, for this very nice introduction. And I would also like to thank Professor Zavrtanik for inviting me and for giving me this opportunity to talk about my favorite topic, which is stars and their final moments. First, allow me to ask a question, to start with a question. When you don't have to answer it out loud, you just think about it. So when was the last time you had a look at the night sky for more than 10-20 seconds? If you are like most Europeans, it was probably some time ago, because most people nowadays, first we have many other ways of entertainment in the evening, including books, television, internet, and also most people nowadays live in or near cities and towns, and we have a problem of light pollution. So from where we live, we mostly don't see anything else but just the brightest stars. To go To see the Milky Way already requires some efforts. We have to go outside the cities, and we can see here in this figure comparison of the night sky quality in 2 different places. This is Črni Vrh Observatory, which is already outside in the countryside. We can barely see the Milky Way, but if we go to some more remote places like islands, we can see the Milky Way much better. For our ancestors, though, it was quite different. They could observe the night sky, they could see the stars, the Milky Way, and they also saw 5 objects which were moving among the stars, and they noticed that they are different. So ancient Greeks called them planets or wandering stars, and there were 5 of them. They also, of course, noticed with their naked eyes sun and the moon, and they used this information for orientation in space and in time. In the direction in which the sun rises and sets, this direction changes during the year, and they could measure the time with that. And also they could orient themselves, where is the east, north, south, and so on. This was also very important for agricultural societies when they started developing about 12,000 years ago, because with these periodical changes in the sky, they could use this to develop calendars, which was of course very important, because when they planted the seeds, they didn't want to plant them too early or too late, and they could not rely on the meteorological phenomena, because sometimes, you know, they're not very regular. So, of course, nowadays we know that one day the unit, basic unit, is due to Earth's rotation around its own axis, and we know that 1 year is the period that it takes the Earth to make one orbit around the Sun. Also, smaller units like 1 month are connected with astronomical phenomena. It takes 29.5 days from one full moon to the next one. So this is the basic, this for the month. And also, a smaller unit, week, has astronomical origin, because there are 7 days of the week, and we can notice from their names in the Latin, or languages which developed from the Latin language, that each day is devoted to one of the objects which we can see with the naked eye in the sky and are not stars. So first one, of course, Sunday, it's obvious, Moon Day, then we have the Mars Day, Mercury Day, Jupiter's Day, Venus Day, and then Saturn's Day. But apart from planets, our ancestors noticed that stars don't change, that their patterns in the sky remain the same, and we call these patterns now constellations. We see some figures from Greek mythology, for example, in them. And up to Renaissance, most people thought that everything in the sky, in the heavens, was completely different than on Earth. It was eternal, unchanging, so perfect stars and the sun were supposed to be perfect spheres without any flaws. So people thought that stars don't have any beginning or the end. But for some astronomers, for example, ancient Chinese astronomers, regularly recorded events in the sky, and they noticed so-called guest stars. They saw objects which appeared in the sky, were there for a while, and then after some time, weeks or months, they disappeared. Of course, some of them were comets, objects in our solar system, but they also noticed new stars, which were called novae, or very bright new stars, which were called supernovae. Of course, they were not new stars, but they were just stars which became, for some reason, much brighter than they were before. Very famous one is the guest star which appeared in 1054, which was visible also during the daytime. And we know now that this was a supernova explosion. And we see at the place where it happened, we see this nice gassy nebula in the sky. And we also know that in the middle of it, there is a special object called a pulsar, about which we are going to talk a bit later. So nowadays, we know, of course, that planets are moving apparently among the stars because they are in our solar system, they orbit the sun, and they appear to be moving among the stars because stars are at much larger distances, so large that we can barely notice their proper motions if they are moving. We also know that stars are born and die, that they have a lifetime, but this lifetime is much longer than human timescales, so we don't see many changes in the appearance of a star during our lifetime. For example, if we compare a stellar life to our life, for example, watching one star for 400 years, since we have telescopes, would be like watching a human for a few hours or a few days. So we wouldn't see any significant change. But we also know that the sky is not really eternal and unchanging. We have many objects that appear to be changing in brightness or just appear and disappear. And that there are many types of so-called transient events. So we call transients everything that is changing rapidly, for example, on timescales from seconds to years. And this is now, with new technology, is becoming a very interesting and also very timely field of research, because we can really see many new things. So this is a film which shows all the supernovae which were discovered in the last 30 years. This is the sky shown in galactic coordinates, so this is our galactic plane, the Milky Way, and you will notice that as years go on, there are more and more supernovae, not because there would be actually more supernovae in the sky, in this universe, but because we have better technology, we can see deeper in the space, and we can cover larger areas of the sky. You will also notice that in some years there appear some bands where there are more supernovae. This is only due to special surveys which were frequently observing this part of the sky. And we see that as the time goes on and we have better and better technology, the sky does not really appear unchanging and eternal, but it is really very active. And these are only supernovae. There are also many other types of transient events, so we can see that if we look, we will see many new things in the sky. We have nowadays, there are several projects which are dealing with observing the large areas of the sky in order to detect these transient events. For this, we need wide field instruments to cover large areas of the sky, preferably even all sky surveys. So on the ground, there were several surveys or telescopes. Some of them are still active. For example, one very successful was the Palomar Transient Factory in USA, then Pan-STARRS in Hawaii, and, for example, Catalina Sky Survey, which served also as the preparation for the next one very big astronomical project, which is the Large Synoptic Survey Telescope, or LSST. It's going to be built in Chile, and it's a collaboration of the USA and many other also European countries. It's going to be an 8-meter telescope, so it means that it can see also very dark, faint objects. It can go to deep magnitudes, and its specialty is that it's going to have a very large field of view for a telescope of this size. Comparing to, for example, other 8-meter telescopes, the field of view of the LSST will be much larger. And due to this large area, large field of view, it will cover the entire sky in 3 days. So it will repeat observations. And this is, of course, going to change astronomy in many ways. One of the big problems will be the software, because it's going to be a huge amount of data, and also for transients, they expect large number to detect thousands of transients in 10 minutes of observations. So an important part of this software will be how to classify them, to see what is which kind of object, and then to have follow-up observations to study them in more detail, for example, with spectroscopy. There are also surveys in the sky, in the space. For example, I will talk also about gamma ray bursts, which are detected with Swift and Fermi satellites. So these are satellites which cover a large area of the sky and detect this high energy radiation which is coming from the universe. But there is also, for example, a Gaia satellite, which is the European project. Its main purpose is to study our Milky Way, our galaxy, and as it scans the sky, it also detects many other transient events which are happening outside our galaxy. What types of transients there are? What are they? What can we see? We can see many variable sources from different kinds of variable stars, which are intrinsically variable because something is changing in the star, and that's why it changes its brightness. But also we can detect some events which are due to just geometrical effects, because, for example, in a binary star, one star can eclipse the other one, and that's what we see as the change in brightness. Or, for example, gravitational lensing and similar. And there are also some extragalactic sources which can change in brightness, for example, active galactic nuclei. These are the centers of galaxies which have a black hole inside, and this black hole is accreting a lot of material, and that's why the centers of these galaxies are shining very brightly. But today we are going to talk only about those which are very energetic and connected with the final moments of stars. These are supernovae, gamma ray bursts, and tidal disruption events. So to talk about them, we need to go briefly through stellar life, how stellar stars form and how they evolve and die. The crucial thing is that the main parameter which defines how the star is evolving is its mass. The composition or rotation is not so important, but mass is the most important. It means basically the higher the mass of the star, the shorter its lifetime is going to be. So everything evolves much quicker for massive stars. So how do stars form? They form from an interstellar cloud of material, mostly hydrogen and some helium. And this cloud starts collapsing under its own gravity. It fragments into special bits which collapse by themselves. And we can see protostars forming in these most dense regions. Stars always form in a group, so in a cluster of stars. So from these protostars, it takes some time to develop into a real star. Real star is a star which has nuclear reactions in its core, so it fuses hydrogen nuclei into helium-4 nuclei. In this HR diagram, as we call it, which is just the plot which connects the surface temperature of the star and its brightness, it takes stars a different amount of time to come from being a protostar to being an actual star, which is then, as we say, that the star is then on the main sequence of this diagram. And we already see that massive stars, for them it takes only about 60,000 years, while for less massive stars it can take hundreds of millions of years to come to this stage. So one thing we need to know is that in the star there is always a battle between gravity, which tries to squeeze the star, and some pressure inside which counteracts to that. So until, if the star is hot, it can have this pressure inside. But then if it is hot in the cold universe, it emits radiation and it loses energy. So it needs to replace this energy to keep the temperature very high by having nuclear reactions inside. But as time goes on, at some point, there is no more hydrogen in the stellar core. So what happens then? Does the gravity win or the pressure win? So this means that when there is no more fuel in the core slightly shrinks, and then the nuclear reactions start happening in the envelope, in the layers around the stellar core. So basically, to make it simple, the star, then the outer layers expand. And the core shrinks even further, and then higher cycles of nuclear reactions start. For example, helium can start fusing into carbon and so on. But then there are two main differences what happens to a star, depending on what its mass is. If you have a low mass star, then the star expands, becomes a red giant, and then after a while it starts fusing helium in the core, and then it expands again. But this time when it expands, it becomes so large, these outer layers are so far away from the tiny core that the core cannot hold on to these layers, to this envelope with its gravitational force. So it starts losing this envelope and it looks like a planetary nebula. And inside there is the core, which is a white dwarf. So this is a star which has a mass similar to our sun's mass, but it is the size of our planet, for example, like Earth. And in this core, the density is so high, 10 to the 9th kilograms per cubic meter, that the gas, the material has special properties, and we call that it is the generate electron gas. And this is then the stable phase. This core can cool down and still keep this pressure, and then it doesn't collapse. So this is then the final stage of this star, and the pressure has won over gravity. For higher mass, the story is a bit different. The higher the mass of the star, the higher nuclear cycles it can go through, because each cycle requires higher temperature in the core. So at the end, the star looks like an onion with the iron-nickel core and layers of other elements above it. So what happens then when there is no more fuel even in the core, because iron and nickel are the final stage for the nuclear fusion? The core collapses in a matter of seconds, and this releases a huge amount of gravitational energy, which then produces the explosion of the star. So the star explodes in what we call a supernova explosion. If we look at the gravitational energy which is released, if we start that the core is some normal size, several tens of thousands of kilometers, and then it collapses to just 10 kilometers, which is the end state of this collapse, then we get a huge amount of energy released. But in this collapse, during this collapse, there is a lot of there is a process called electron capture. So the density is the matter is so dense that protons and electrons combine to neutrons. And this releases a lot of neutrinos, which then mostly carry away all the energy. In the electromagnetic radiation in the light, we can only see about 1% of the energy released. And then this explosion fades away on time scales of months, for example. This is one figure which tries to explain this. So we have a star which explodes, becomes very bright, and after a while it fades away, but if we wait for tens or hundreds of years, we see this envelope expanding. Velocities with which these envelopes expand can reach up to 30,000 kilometers per second, so comparable already to the speed of light. Here is also one nice example of two supernovae occurring in a galaxy. This was the first one in January 2008, and then the second one appeared here. And you can also notice that the first one slightly already faded in the meantime. And this is a plot showing this fading on a time scale of, let's say, 2-3 months. Very nice example of the remnant after the supernova explosion is this one. This was observed by Kepler, and it's the last observed supernova in our galaxy. So, because these supernovae are so bright that we can also observe them in other galaxies. So what happens with the core? We only said that the core collapses. It can go in two different ways. It can collapse and become a neutron star, which means it is about the size of the 10 kilometers, composed of neutrons, if we simplify a bit, and has a maximum mass, for example, 2 to 3 solar masses, and it is similar in a way to the white dwarf that we mentioned earlier, but instead of electrons, we now have neutrons. And we have this degenerate neutron gas, which then with its pressure counteracts the gravity, and we can say that the pressure has won the battle. These young neutron stars often have high magnetic field and are rotating very quickly, and they're then seen as pulsars. So they emit light in these two cones, and if we are in one of those cones, then we can see these pulses of light. But the other possibility is if there is too much mass inside the core, more than 2 to 3 solar masses, then this pressure cannot fight gravity. Gravity is so strong that the core collapses and becomes a black hole. So black hole is the region of space where, from which we would need higher velocity to escape than the speed of light. And this is defined then as the black hole horizon, which is connected with the mass of the object. So in this way, we see that in supernovae, we need to understand supernovae, we need to connect different areas. We need to know about stellar evolution, we need to know about general relativity, because we are dealing with neutron stars and black holes, and also with high energy physics, because we had lots of neutrinos, huge energies, a lot of nucleosynthesis, and many things. So there are different types of supernovae. One are what we were talking about now are core collapse supernovae. There are several types of them, but then there are also type 1a supernovae, which we could call a special end of a star. So in this case, we had a binary star. One was, for example, a white dwarf, and another one is the normal star. But they are so close together that the white dwarf is stealing matter from the normal star. It accretes material and it gains mass. And when it comes to 1.4 mass of the sun, it becomes too heavy and unstable and then explodes like a supernova. The core shrinks into neutron star and explodes their envelope, the other parts are expelled. So these supernovae are very important because they have all about the same brightness at the peak level, and we can use this information to measure how distant they are. So if we know how much energy they emitted, and we know how bright they seem to us, then we know how distant they are. So these are called the standard candles. And in astronomy, and this was very important also in cosmology, because with the help of type 1a supernovae, they measured that the universe is expanding more and more rapidly. Other current topics in supernova research are, of course, connected. There are many different questions in stellar formation and evolution. There are, for example, interesting papers lately on shock breakouts, so how this explosion and the shocks that form then break out. And also, for example, natal kicks, which are explosions which are not spherically symmetric. It can happen that the core is ejected from the envelope and also from outside of its own galaxy. So this is one type of stellar death that is very violent, we could say. Then another one are gamma ray bursts. So as the name suggests, these are the bursts of gamma rays. And as gamma rays do not penetrate the Earth's atmosphere, we need satellites to detect them. So we see that gamma ray bursts are occurring everywhere in the sky. Isotropically, they happen about range 1 per day. They are unpredictable and very short. They can last from less than a second to hundreds of seconds, sometimes even thousands of seconds. So if we observe, we get the information from the satellite that a gamma ray burst has appeared and where in the sky it has been. And then if we observe this part of the sky very quickly, we can notice also in optical and other wavelengths, so-called afterglows, a point source of light, which then fades away on a time scale of hours, sometimes also days or weeks. So you will see here one appearing like a new star, and then disappearing. And if we observe it with this location with a bigger telescope, we can see it, but it fades again. So we have to be quick, and if we are quick and we use larger telescopes like Hubble Space Telescope, we can also see that where they are happening, that there are galaxies. Some of these galaxies are very far, that's why they are just like a smudge in the picture, but we see that there are different types of galaxies, and we can then use ground-based telescopes to take a spectra of these galaxies and measure so-called cosmological redshift, which enables us to determine distance to these gamma ray bursts. And once we know the distance, we can calculate what is the energy needed for these events. If we assume that the energy is released in all directions, isotropically, then we come to a very large number, which means that which is comparable to the rest mass of the sun. But from some observations, we know that the emission is not isotropical in this case, like it was in supernovae, but it is focused in two opposite jets. And we only detect these gamma ray bursts when one of the jets is pointing toward us. And the energy that we need is then, the energy requirements are not so severe, so we need about, again, 10 to the 40 or 10 to the 46 joules of energy. So this is comparable to what we need in a supernova, but that in this case it is released in a much shorter period of time than in supernovae. So maybe just to how that you can imagine what this energy means. If we take our nuclear plant in Krško, if it would operate like it is operating for the whole age of the universe, 14 billions of years, it would produce so much energy as our sun releases in 1 second. And here, if we would take our sun and take all the energy which will emit during its lifetime, we will get the same amount, or approximately the same amount, as this gamma ray bursts are emitting in 1 second. And we know that we have two types of gamma ray bursts. We can see that if we look at the number of bursts and their duration, we can see that there are two groups, and the division is about at 2 seconds. So we have those who are shorter than 2 seconds and those who are longer than 2 seconds, and we think that there are two different scenarios how they are produced. For the short gamma ray bursts, we think that they are produced by the merger of two neutron stars, two very compact neutron stars. They spiral together because they lose energy due to gravitational radiation, and when they come together, they merge into a black hole and produce these two opposite jets in the direction of their angular momentum. For this scenario, we don't have direct evidence, but we have indirect evidence. We see that these gamma ray bursts are occurring in galaxies where there is not a lot of star formation, where the stars are old, and this is exactly what neutron stars are. They're old. The other type of gamma ray bursts, long gamma ray bursts, we think they are produced in a explosion which is similar in some way to supernova explosion, but that it is produced in two jets. So the core of the star collapses to a neutron star or a black hole, and two opposite jets drill through the stellar envelope, and then they expand practically with the speed of light into the space. For this scenario, we do have some evidence. So we know that there is a connection between gamma ray bursts and supernovae. For example, when we observe the light from the optical afterglow of a gamma ray burst, at about 20-30 days afterwards, there is a little bump in the light curve, which we call a supernova bump, because if we take a spectra of this light at different stages, for example, in the beginning, we see that it is a parallel, it is a straight line in this plot. And then the later we will take the spectra, the more the spectra looks like a supernova spectra. So we think that these jets immediately drill through the star, and we see this jets emission, and then afterwards the rest of the star explodes, and we see this as the supernova then. We use different instruments to follow up and observe these events. We want to see them, we want to combine information from different wavelengths, from all wavelengths that we can, so that we can get a broader and more proper picture. In our group, in which there are people from Slovenia, Italy, and United Kingdom, we use a network of robotic optical telescopes. The most important one that we use is on La Palma. It is called the Liverpool telescope. You can see it here. It has a 2-meter diameter mirror. So this is not huge for now modern telescopes, but it is the largest robotic telescope in the world. Why robotic? Because we need that it reacts very quickly. So when the gamma ray burst happens, for example, a satellite detects it, sends the alert directly to the telescope, which then turns to this point on the sky where the gamma ray burst has happened and starts observing immediately and sends us pictures in real time. So maybe now we can look at the theoretical picture. So what do we think, how this emission is produced? For example, we have a star which is quite evolved, and the core is collapsing to a neutron star or a black hole, and in about 10 seconds, these two jets drill outside from the inside to the outside of the star. If we are in the right place, we can see this emission, which is now produced because different shells of material in this jet are catching up, accelerating electrons, which then emit synchrotron radiation, and we see this as a gamma ray burst. When this jet then slams into the material around this star, it slows down a bit, and then it produces the afterglow emission that we see. And we only see it, of course, if this jet is pointing towards us. So this is a similar animation, which sees that the internal shocks that we call are accelerating and then shining brightly in gamma rays, and then when this outer region collides with the material around it, then produces the afterglow emission. So the optical afterglows that we observe are very diverse. At the early time, you can see that some are very bright, some are so bright that we can observe with the naked eye, or could if we knew where to look. But some are so dark that not even with the telescopes we can detect them. So there is about 100,000 factor between those that we observe. So we have to be ready for very bright one and also for very dark one. There are many open questions in gamma ray bursts today. So what exactly are the progenitors, types of stars which produce them? What is the central engine? Is it a magnetar, a neutron star with a huge magnetic field, or is it a black hole? What is how the energy is dissipated and particle accelerated? What is exactly the radiation mechanism? Why are afterglows so different? Some very bright, some not bright. And one of the very important one is the role of the magnetic field. So we have some plasma, and there must be some magnetic field involved. So to answer this, it is important that we measure, if possible, polarization of the optical afterglow. So polarization is we could say it's the percentage of light that has electric field in some particular direction. And I won't go into details here, maybe later if somebody is interested. We expect that the electrons which are in these jets, that if the magnetic field is oriented, the electrons will produce polarized light. So the polarization degree should be around 70% if we have a very nice, large-scaled and ordered magnetic field. If not, we can expect much lower polarization. For example, this would be that the magnetic field is ordered, and we expect high polarization. If magnetic field is random, but we are observing this jet just along the edge, we can expect up to 20% polarization. And if we have a special random patches of magnetic field, then polarization should be around 10%. So to answer this, we put a polarimeter on the Liverpool telescope. The first version was this Ringo polarimeter, which produced, from each source, it produced a ring of light. That's why it was called Ringo. And we measured the upper limit for polarization of 8%, which meant that in this case, for this gamma ray bursts, polarization was not high, so magnetic field was not very important. But in 2012, with the new version, the Ringo 2 polarimeter, we measured the polarization of afterglow, which faded like it's seen here, and we could measure the polarization. It was about 28% early on, and then it faded to about 16% later on in the next 10 minutes. But polarization angle stayed approximately the same, and this was the indication that we in this case, that we are dealing with a large-scaled and uniform magnetic field, which is somehow connected with the central engine. And this was the first measurement of the early temporal evolution of optical polarization. Other measurements were made at a much later time with larger telescopes. Now we have the third version of the instrument installed on the Liverpool telescope, which can measure polarization simultaneously in 3 different wavelengths regions, 3 different filters. We also use some larger telescopes because when the afterglow fades, we need bigger machines to see it. We also use larger telescopes to do spectroscopy of the afterglow or the host galaxy, and also to do polarimetry, for example, when the source is fainter. It is very useful to use for example, we are collaborating with people who use the X-shooter instrument on the very large telescope in Chile to do spectroscopy. But we also recently measured, in a special case, with the VLT, we used VLT to measure circular polarization of this afterglow, which you see how it faded away. About 3 hours after the burst was detected by satellite, we observed and we measured linear and circular polarization of this afterglow. We found that the ratio was about 0.15, which may seem little, but it was actually much too high for theoretical models, which are predicting that this polarization, this ratio should be much smaller. So this is now a question for theorists how to explain this. We did exclude that this is not due to some dust scattering or plasma propagation effects, but this is actually intrinsic circular polarization. So one explanation could be that about the details about how electrons are distributed in these jets. If we compare this measurement with the optical circular polarization for quasars, we see that this is much higher than for any other source, and it is also at the highest redshift. So this is the most distant event or object for which circular polarization in optical was measured. And also, if we use spectroscopy at the VLT, we can detect many absorption lines in this spectra, which tell us many things about the host galaxy in which the gamma ray burst occurred, but also all the material through which this light was propagating in order to reach us. So, for example, because gamma ray bursts are so bright, we can detect them even if they happen very far away. For example, even from the first stars, which probably occurred about 5 million years after the Big Bang, we can already see a gamma ray burst coming from there. So we can detect all the material through which this light was propagating, so we can use gamma ray bursts as cosmological probes. So to study if galaxies were different at different cosmic epochs, or also to see if the mechanism which produces gamma ray bursts was different. So maybe in the early universe the stars were different composition, different size, and they were producing different gamma ray bursts. In this case, in 130427A, this case was very bright, and it happened quite close to our galaxy. So we can see that if we compare, these are the gamma ray bursts, their energy, and the redshift, or so we can say distance to these events. And we see that mostly other events, we see that in a recent universe, it's appeared that gamma ray bursts are all weaker than those happening in more distant part of the universe, so which happened earlier in the universe, in its evolution. But this special case, in this case, we could measure that this burst is, if we compare it, its energy is quite comparable to the brightest burst that we see in distant universe, so in the early universe. So we see that in this case we show that the mechanism is not really different, that it seems that it was the same. Why are gamma ray bursts important? Why do we study them? Of course, to study stellar evolution, it is not still clear what is the difference of a star, which star makes supernova explosions and which stars make gamma ray bursts, how this is connected. Using them at the different times, in the different distances from us, different ages of the universe, we can study star formation at different and host properties at the different stages of the universe development. There are some efforts also to use them as standard candles in cosmology to determine also the expansion of the universe, similarly as in supernovae. And of course, there are regions where we can study what happens when we have a very strong gravitational and very strong magnetic field. So these are the circumstances that we cannot reproduce on Earth. And also, of course, with all this huge energy released, we are dealing with high energy physics, and a lot of particles are probably produced, and some suggest that they might be interested also as multi-messenger sources. So this means that they could, for example, merger of two neutron stars could produce a specific gravitational wave signal, or that there could be some cosmic rays produced, or neutrinos. And so this will be interesting to see in the future. And then the third type of stellar death, if we call it, is not connected so much with their evolution, but with dynamics and their bad fortune. We know that some stars are so unfortunate to wander too close to a black hole, and then they get disrupted. We know that supermassive black holes exist in most galaxies in which they measured. We know that there is one in our galactic center. We see here that from the orbits of these stars, we see how this orbits changes and we know that in this little part here, there must be a mass of about 3 to 4 million solar masses. And similarly, there are in other galaxies black holes which don't emit a lot of light, or they don't eat so much material that they would shine brightly, these accretion disks around them, but are just dormant. But then if a star comes close to them and it's tidally disrupted, as we say, then it can produce a very bright flare. So what is tidal disruption? You are familiar with the Earth and the moon system. So the moon and also the sun cause that the Earth's shape is slightly changed because of the tidal effect. So now imagine that Earth is a star and that moon is a black hole. So if the star comes too close, it will get completely disrupted. But this only happens if, depending on what is the mass of the black hole. If we have a small black hole, then the star will be disrupted outside the black hole, and it will get shredded in some gas and streams and so on. If we have a mass, this can happen far away from the black hole in the sense that we can treat such event in Newtonian dynamics. We don't need to go into special relativity. If a mass of the black hole is about 1 million solar masses, then this tidal disruption is happening in the region where we have to take into account all the general relativistic effect, and this complicates the picture then further. But if the mass of the black hole is very large, then the star can fall into the black hole without noticing, and then it gets disrupted already only when it is already outside. So in this case, I don't know which ones are more dangerous. So to study this, of course, we need to know stellar dynamics, so how the star comes so close to the black hole. We need to know general relativity. Again, high energies are released because when the star is disrupted, we again are dealing with very high energies. And in order to make proper simulations, we also have to take into account hydrodynamics. So there are several events that were observed and were interpreted as the tidal disruption event. One is, for example, this one. We can see a picture from 2009 with the in UV light and invisible light. And here we see it in 2010. We see that here there is no source visible, and here it is very bright source. And here it was a small galaxy, which then brightened and become much bluer, which means that it's much hotter than it was before. So something was happening inside. And this is the light curve of this event, and it was from the spectra and how it was fading. It was consistent with a tidal disruption event. So the star that was disrupted and eaten partially by a black hole. This was the first event that they observed, actually, the rising part of such an event. Usually they start later on, observations. And there are also several events which are interpreted as tidal disruption event, but in a very relativistic way, as we say, that when the star is disrupted, also two jets are again produced, similarly as in gamma ray bursts, but the proper mechanism is not completely understood yet. And we see here, for example, that this event really happened it seems that it happened in the center of a galaxy, so where you would have the black hole. And this event was much studied in details, and after about 500 days, its luminosity, which was doing many things and decaying mostly, but then it suddenly dropped by several factors. And this was then believed that this is due to this jet turning off, so that the accretion stopped and the jet turned off as well. So, to conclude, there are several projects, or some already ended, some are still going on, and where people are trying to observe large areas of the sky. They use wide field of view instruments, repeating observations, for example, like every 3 days with LSST, it's going to be, and so to cover as much as possible. And just for the LSST, for example, to tell you a few numbers, how many of these transients are expected. For example, for tidal disruption flares, they expect to detect about 6,000 per year, and supernovae 20,000 a year. So this gives you a sense that how difficult it's going to be to study all this, if not with humans, but we will need computers and some automated procedures for many of this. So to conclude, I hope I convinced you that the sky is changing, and that although our ancestors thought that the skies and stars are eternal, we can, using modern technology, actually observe all this development in real time in front of our eyes. Thank you.
Thank you, Andreja, very much for this very interesting and nice overview. It's very nice to find out that although people have been gazing at the skies ever since we remember it, this is still a very lively and scientific field with a lot of things going on and a lot of things we don't yet understand. So perhaps this is a time for a few questions from the audience. Taken that there are many people who are actually involved in astroparticle physics in this room. Okay, I suppose we can start with the questions, and when the technology starts working. Yeah. So please.
When was the Big Bang happen last? The Big Bang.
The Big Bang?
Yeah.
Yes.
The first supernova. When it was happened last time? Is any record?
You are asking me when the first supernova explosion was recorded in human history, you mean?
Yeah, in the human history.
I don't know exactly, but I guess it was from Chinese astronomers or maybe even some other ancient nations, because there are many historical things that sometimes they draw a star on some picture in a cave, or I don't know, so it's difficult to know exactly. But I know that Chinese astronomers recorded several tens of supernova explosions.
Let's see. Well, the next question is, what about these black holes? I mean, I guess I've been involved in this cosmology 30 years ago, and then I left because I couldn't find anything through my naked eyes. So I changed my field and I went into the fluid dynamics, right? So these black holes, I guess, is almost 10 to the power 8 black holes exist in the universe. And each of them as big as 3 times or maybe more times the radius of the sun. And these are all exist in the universe. Do these activities happen through black holes also when the 2 black holes come closer to each other?
You're asking me if 2 black holes
When
merge?
they come closer to each other?
It is possible. Well, they think, we don't know exactly, but we think that also if 2 black holes merge, that this could also produce a gamma ray burst, short gamma ray bursts, perhaps. But
Okay.
as I said, also for this merger scenario, we don't have any specific proof. It's just a circumstantial proof that this is correct view.
Thank you. Thank you very much. It was really very interesting talk.
Thank you.
Okay, more questions? Yeah, Primož.
Thanks for this nice talk. So the motivation behind the polarization measurements was, if I understood correctly, was to find out what is the radiation mechanism. Is that correct?
What is the role of the magnetic field? That was because there are different models. In some of them, the magnetic field is just produced locally and doesn't play a huge role in how these jets are evolving and expanding. So this was then our idea to test this, because there are different predictions. And what we find is that in this case, the magnetic field was important, but not on the dynamics, but on the polarization and on that it was ordered, but its strength was still not so high that it would actually influence the expansion of this jet.
So but in one of the slides, you said that the radiation mechanism is still an open question, or?
Yes, well, the basic...
I mean, my question is, can you measure anything besides polarization, like the longitudinal coherence or the phase structure, transverse phase structure of the radiation emitted, or?
Yes, they're studying this in high energy gamma rays. For example, from Fermi, they have very nice light curves, and then in different channels they compare what is happening, how are the variations connected. So, but this is not my field. I know that there are many different papers about this. The basic idea is that the radiation is coming from electrons, which are radiating synchrotron radiation, but there are many different, if you look at the spectra of gamma rays, there are examples where you need some inverse Compton scattering or synchrotron self-Compton.
Sure.
So it's,
I mean, I can understand that there are many models that could...
yes,
yeah, okay.
and there are models, for example, that if the magnetic field is very important, that you have some reconnections, and it's getting more and more complicated.
Okay, thanks.
Okay, one more question, perhaps?
Good evening. It was a really good experience to listen to you. I had just one question as a non-expert. So you're saying that the universe is expanding still, right? So is there a turning point somewhere along the way, or we don't know that yet?
You mean if it is going to stop and then... No, it seems that it is accelerating in this expansion. So it is expanding quicker and quicker, so it will not stop.
Okay. Thank you.
Black holes eating up all
Okay. Well, if there are no more questions, oh, there is one. Okay. Yes.
Andrea, with gamma rays you don't have problems. When gamma rays are traveling through the universe, you don't have problems with attenuation and scattering and all that. How far or how deep in the universe we can see these days with the most modern equipment we have?
You mean with the in optical or in just in general?
For example, high energy gamma rays would be one possibility. How deep you probably see very deep in the universe.
Yes, with the gamma ray bursts, because they are so bright, we can see the record is around, there are two very high redshift bursts, one at 8 point something and 9 point something. So this means around 400 million years after the Big Bang already. So this would be really the first stars that would, so now it is 13.7 billion, so this is really then 13.3 billion light years away. So this is why the gamma ray bursts are so special, because they are so bright that we can see them so far. Similarly as the Hubble Space Telescope with the deep field, ultra deep field and extreme deep field, when they're observing one particular area of the sky for days and days, they can see also to about this size. They can detect little dots that they think they are first galaxies that were forming them.
So, but the most distant parts you see with the high energy gamma rays are not accessible to other methods, or I mean, invisible you probably don't see that far because of the...
No, invisible, no. Well, the Hubble space is then using the infrared because everything is stretched due to the expansion of the universe. So I don't recall that they would see further than the gamma ray bursts. Maybe some quasars, I don't know.
Okay, so thank you very much for your questions. I do encourage you all to ask more questions informally at the ground floor after the conclusion of this session. Okay, thank you very much, Andrea.
Thank you.